Turns out that the neural netverse seems to have more than just one tree. There's a boson tree, and then there's also a fermion tree. And of course, there's this weird tree down here. I guess it's the Higgs tree. And the idea here is that the bosons are decomposition. So you get like a 1 times 1 equals 1 plus 0. A 2 times 2 equals 3 plus 1. And a 3 times 3 equals 8 plus 1. And this just gives us straight up the bosons. So we can get like a singlet here. We can get this doublet here. There's 3 of them. And then we can get 8 gluons. So we have all the bosons here just from the decomposition of these groups, which is fine. That gives us the branches for our decision tree. But then we have the fermion tree. Well, the fermion tree kind of acts with this type of situation where you're going to take like a tuple, and the tuple is like this input where you have the color, uh, a weak, and a hypercharge, weak isospin. And then over here, we can see what the outputs would be. It's either going to be true, 1, false is 0, or you're going to have some charge. Well, if it's true, then you're going to have a charge. And of course, charge is the readout charge that we can calculate from a little equation here, the T3 plus Y. And so here's some examples where you can see that T3 is going to be either positive a half or negative a half for these two particles. And then you get the hypercharge is negative a half, and then you can get the charge from that. So this is kind of how like you can input a tuple into the neural netverse, and then you're going to output some fermion charge, or rather a tuple with a charges as well. So here are some of the outputs that you can get from the fermion tree. They're going to be basically the leaves on the branches, but notice they're not really attached yet, they're just leaves. But here are the leaves. They're spin 1/2, and you can get 1, 1, 1, 2, 3, 1, 3, 2. These are just the valid entries that we can have for our tuple. So you select one of those, you select one of those, you select the appropriate one of those. It's just if-then statements. And then, you get this, where you can have the different particles, neutrinos, electrons, up quarks, down quarks, leptons, and stuff like that. And the Higgs down here, the Higgs is different because there is no decomposition, there is no tuple rule. This has been calculated kind of by hand or subbed in there using a Yukawa coupling. And so this is a little bit different. But the Higgs can kind of be like the stems that are going to attach the leaves to the branches. And this is through the Yukawa coupling here. Yukawa coupling. So this is just another way that we can sort of take a look at the trees, decision trees that are coming out of the standard model in our neural netverse. Here's some interesting combinations where you can take mesons by plugging in a 3 by 3 over here, and so when you get this, you can also get baryons by shoving 3 quarks together. 1, 2, 3, and you get some kind of decomp like this. So it's just kind of interesting how we're able to kind of put this into the form of a neural netverse and get some outputs from our inputs after they go through these activation layers with the anomalies. This is very interesting. The boson tree,